Okay. I sent out the next quiz, right? And there was a question about the due date. Did I put the due date on there? I think it's like next, not next Monday, right? When is it? It is next Monday? It is? Really? Oh, okay. Okay. Well, I guess that's the right due date. I'd have to go back and look at the quiz to see what was the last problem on the quiz. Anyone have it with them? No? You have it right there? Okay, let me look real quick. Volume of the ball, drilled out radius. Yeah, okay. Yeah, it's due next Monday, a week from today. We do not have class this Wednesday. It's Faculty Development Day. So if you have any classes that meet here before 5 o'clock, they're canceled. If you meet after 5 o'clock for any classes, I believe they're still on. But just check with your other courses. But we will not be here on Wednesday, all right? So this is our only day this week, so let's try and get to work. Any questions over anything? Homework or the quiz? If you have questions on the quiz, contact me, or if you have anything off right now, I'll entertain the idea of discussion, but no, not yet. Okay, well, there was something in 12.2 that I think breezed over this. I remember doing this where we were saying that if you do a double integral over region D, that if that region D is the union of two regions, then you can break up the region D and do two double integrals instead of one. But I don't recall that I mentioned this. And this is actually a really nice result. So I want to make sure everyone is aware of this. If you have a double integral over some region D, then the region on the ground is like the shadow of you're looking down, there's a surface, you're looking down onto the ground, trying to find the volume below that, right? Yes? Well, if your function is the constant one function, then it's just a flat sheet, isn't it? Just a horizontal plane. So the volume straight down, the height of each of those rectangular boxes that we make from the double integral, y'all know what I'm talking about, right? That's the other section, 12.1. I know you said you know what I'm talking about, but let me just get back to the picture. There we go. Remember each of these rectangular boxes that we had? We're doing infinitesimally many of them, right? Well, if the function on top is constant, then each of those heights is 1, right? And so the volume of this box is just its infinitesimal area times 1, which is just its infinitesimal area. So we add them all up, then we're getting the area of each of the infinitesimal pieces on the ground times 1 is just the sum of all the areas, right? Which would give you this formula, that the double integral over D of the constant 1 function should just be the area of the region you're integrating over. So this is another way of finding areas of curves. And if you have two curves, you can find the area of them by converting it to a double integral instead of doing some of the stuff we did in Cal 1. Now this is going to become useful in the next section, but I just want to point it out now. All right? So I forgot to mention that last time. And I believe we were done with this section, and we were going to start polar double integrals and polar coordinates, so that's where we're going to pick up. So up to this point, we have double integrals over 3 types of regions, right? We have the good old rectangle, which is the very, very nice case where a double integral would go from A to B and then C to D, and we could switch the order of integration. It didn't matter. And then we said type 1, where our x's are between 2 constants, our y's are between 2 functions of x. We have type 2, where it's the other way around. Our y's are between 2 constants, and our x's are between two functions of y. But there are some regions in real applications that are neither one of those. For example, polar regions or circular regions. So we're going to first do a quick review of polar coordinates. We all know that in the Cartesian plane, which is two-dimensional space, the way that you get out to a point in the Cartesian plane, you can look at it different ways. To get to that point, you could travel along the x-axis a certain distance and then travel a certain distance parallel to the y-axis. And those are called Cartesian coordinates. The x and the y give you your directed distances in both the x direction and y direction, right? But the other way you could get to that point is to instead of going out x and up y, you could just say, look, point out the x-axis, turn by a certain amount, and walk out a certain distance. And that would get you there also, right? Well, to get to this point then, in Cartesian, you need two things, don't you? X and y. In looking at it in this way, where you rotate and walk, you still need two things, right? You need how much you rotate by, you need how far you walk. So you still need two things, two pieces of information to get to the point. It's just that information is different than it was in Cartesian. When we do it with the angle and the distance, that's called polar coordinates. Yeah, how many of you have seen polar coordinates? I know some people don't, so it's okay. So if we use this right triangle as our basis for getting to this point, construct this right triangle, there are many trigonometric identities here, right? We know by Pythagorean identity, x squared plus y squared is r squared, right? We have relationships between theta and the sides, like cosine theta is adjacent over hypotenuse, so cosine theta is x over r. Sine theta is y over r. Tangent theta is y over x, right? All these different trig relationships gives us what we call the relationships between Cartesian and polar coordinates. There's the Pythagorean identity, x squared plus y squared is r squared. This one was that cosine was x over r, but if we multiply both sides by r, we get this. This is a key one. Our x-coordinate can always be determined by knowing the radius r, how far we walk out, and then the angle that we rotate and then taking cosine. The y-coordinate, same way. Solve this for y. Sine theta equals y over r, solve for y. And then where does this come from? Well, we said tangent theta was what? Y over x? So take the arctangent on both sides of that equation and you get theta is arctangent of y over x. So these are the things that we can use anytime we want to switch from one coordinate system to the other. These are the relationships that we have. Okay. Now, remember what a rectangle looks like in Cartesian coordinates, right? A rectangle in Cartesian coordinates, our x was between two constants, right? Our y was between two constants, and it was a traditional rectangle. Like if you handed a picture of a rectangle to a 5-year-old and you said, what shape is this? They would say, maybe, I don't know, would they say rectangle, 5-year-olds? Probably. I don't know, whatever. But I mean, most people have an idea of what a rectangle is, right? Okay, but that's a Cartesian rectangle. The x's are between two values, the y's are between two values. Now we're going to look at a rectangular polar region, which is not the same. If we say, here's our picture in two-dimensional space with Cartesian, but what if we say we want to look at all of the polar points where our theta, okay, is between two constants, alpha and beta, and our r is between two constants? What would that look like in two-dimensional space? Well, this is it right here. Okay, look, my angle theta goes between two constants, right? In this case, it looks like 0 and something, right? Every point that's between there, and my radius looks like it goes between what? 0 and something? So my radius is stuck between two values, my angle stuck between two values. That's a rectangle in polar coordinates. That's a rectangular region. Now I can change my restriction on the radius. So maybe my radius is now stuck between two constants, but not 0 anymore, right? This is you know, maybe the radius is 1 and 2, or 2 and 3, or whatever it is, but between two constants. And I could also change my angle, maybe something like that. That's a rectangular region in polar coordinates. Do y'all see it? Now, go back to what we learned before this. Is that a rectangle in Cartesian coordinates? No. So we couldn't do it with that sort of double integral, right? We couldn't look at that as a rectangle. Is it type 1? Well, are your x's between two constants and your y's always between two functions of x? No, this curves around itself, right? Fails the vertical line test. I mean, it's not going to be a function of x, right? Can't do it that way. And then how about the other way, type 2? Try and go this way? Same problem, right? So this is not a rectangle. It's not type 1. It's not type 2. So it's its own animal, and that's why we study it, because there are a lot of things in the real world that, you know, think about a, I'm just looking at this right here. Okay. First thing that comes to my mind is like a, you know, a cylinder, right? Use like a pipe or something like that. And maybe you cut the pipe off at an angle, and you're looking at that pipe. You're trying to find its volume, right? So you've got this thick lead pipe or something. You cut it at a certain angle, and you want to know its volume now. So the cut is like a plane, and you're looking below that plane, but above this region. Do y'all see that? So that would make sense that you would want to be able to integrate over that. So polar coordinates is perfectly suited for something like that. Questions? Okay, no problem. All right, so double integrals over polar regions. Let's go back, and sorry about those little keyboards. They accidentally got copied when I did this, and they're there permanently. Remember with our Cartesian double integral, we had some region R on the ground, and what we did is we cut that rectangle up into little infinitesimal areas, right? The width was dx, the height was dy, and so that little dA right there came from just multiplying length times width, or width times height, however you want to look at it, right? Yes? All right, now in polar, boy, that's a terrible picture. Why isn't, that is super blurry. It's crystal clear on my screen. Not sure why that came out so blurry. So I'm going to get to this in a second. I want to remind you that if you have an arc of a circle, so this is R and this is R, so this is a circle that's just been swung through a certain angle, that this S right here we called the arc length, that S was equal to R theta. That's a formula from pre-cal. Arc length is R times the angle. And what's the one stipulation about this formula if you're going to use it? There's something you have to be careful with. You have to be in radians, exactly. This theta right here, if they give you like that's 13 degrees, and that's 4, this is not 4 times 13. You have to convert the degrees to radians, and then you can use the formula, all right? So I'm going to need that to convince you of this. So Cartesian, we cut the ground up into little rectangles, right? And that little dA was the dx dy. Here, we're going to take the ground, we're going to cut it into little rectangles. But little rectangles in polar coordinates are not little rectangles in Cartesian. Well, I just showed you what they look like. So do you all agree that this little red thing right here is a polar rectangle? Yes? It's part of a polar region. It's a polar rectangle. And imagine it's getting like infinitesimally small, right? I want to approximate what the area of that would be. Well, it's almost a rectangle, right? It almost is. If we go infinitesimally small, that thing is closer and closer to like a true Cartesian rectangle. And so the area should be approximately the length times the width, which would be this little dr times this, well, the green piece times the red piece, approximately. And then in the limit as we let it, you know, the number of these go to infinity, it should be exactly that length times the width. You all buy that? Yes? Yeah? Okay. So why is this dr? Well, remember, our r is between two constants, right? R is between two constants. So as we move through and we let R change, then each little change is actually a change in the radius, right? So it's an infinitesimal little dr. So this width right here is dr, just like before it was dx, wasn't it? Now this, though, is not d theta. Okay, that's the difference. Is that d theta is the change in the angle, isn't it? The angle is not the length of this side. So we need to find a relationship between d theta and this side, and that's where this comes in, right? If I replace this right here with d theta, then this form, and the radius is some distance, right? Then this becomes, this arc length is what? R times d theta. So this piece right here is approximately r times d theta. Y'all see that? And now if you multiply those two together, then in our formula, the dA that used to be dx dy, because we're in polar coordinates, now becomes r dr d theta. Or we can switch it. The order doesn't matter here, as long as the theta and r are between two constants. Just like the x and y order didn't matter if we were between constants. So, what's happening is that if we have an integral in Cartesian, and we want to, Cartesian, so it's in terms of x and y, and we want to convert it to a polar double integral instead, we're going to have to do a couple of things. First of all, everywhere we see x's, we have to convert them to r's and thetas, so somehow the x converts over. Then everywhere we see the y's have to convert over, and then the dA becomes r dr d theta instead of dx dy. Notice that r, right? That r is our variable of integration. I mean, look, it's like dr's here, right? We have r. It's almost like having an x like an x would have to be added to a regular integral. It's the actual variable appears. So converting from Cartesian to polar, you always get that r to pop out. It's always going to be there. A little r is going to appear in your new integral, your new double integral. And that, I'm going to beat that into you, okay? I'm going to just beat the r into you, because that's one of the biggest mistakes that people make, is they forget when you go to polar, you always have to put the r in there. Last Cal 3 class I had, they got it. I don't know, they all finally, I mean, it didn't even take time. They just never forgot the r. Other Cal 3 class I've had before, like I always have students forget the r, and then, they turn the test, they'd be like, oh, I forgot the r. They knew it right after they saw it. They forgot the r. So it's just one of those things. Now later on, we're going to have another, we're going to have other stuff where we convert instead of from Cartesian to polar, we just do some other conversion to some other coordinate system. And every time we convert from one coordinate system to another, we're always going to have something pop out, and we'll be able to figure out why it is and how to compute it, but that's later on, all right? Yes. Because if we have an arbitrary, radius, we swing it through some angle, that length is always the radius times the angle. Always. This is the formula from pre-cal, right? Then, when we come over here, and I want to try and figure out how long this red arc is, that's an arc length. That's S, right? What's the radius? Well, it's however far out I am, which is R. And then this angle is actually my infinitesimal change in theta. So that's my little d theta. So theta there is actually d theta. And then r is still r. So that arc length is r d theta. Sure? Okay. All right, so where are we going with this? Here's the formula, right? If r is a polar rectangle, you start out with a traditional double integral in Cartesian. The x gets converted to what? R cosine theta. That's our conversion from Cartesian to polar. Our y gets converted to r sine theta. The dA turns into r d theta dr. Notice the order of integration here. The a and the b are the outer limits, so they go with r. The alpha and the beta are the inner limits. They go with d theta. Notice the r in the formula, right there. All right, so let's see how we can use this. Find the volume under z equals 3x plus 4y squared on the region bounded by x squared plus y squared equals 1 and x squared plus y squared equals 4 with y greater than or equal to 0. So here's the picture. I've already given you the picture, but let's see if you would be comfortable with that. X squared plus y squared equals 1 is a circle, right? In two-dimensional space, circle radius 1. Then you have x squared plus y squared equals 4, circle radius 2. That's this one. You want the region between those, but you also want y to be positive or 0, which gives you everything up, right? So that creates this region right here. We good with that? Think you could draw that yourself? All right, now this is that region in three-dimensional space sitting there on the ground. We have a surface above it, just like we did before. This surface, what does that look like? Well, it looks like this, okay? That's the surface. It's actually sitting above it, and part of it's below it. Do y'all see that? This part over here, our region is above the surface. Over here, it looks like the surface is above our region. So we're going to imagine finding the volume between our surface and the xy plane. Yeah? Understand geometrically what's happening? Let me just get that solid in there. I'll pull the surface out. So there it is right there. Part of it's above, part of it's below. Trying to find that volume. I imagine that in different engineering applications, shapes like that would come up, more often than some of the crap we've been doing, right? I mean, this seems more real world applied than it would be some of the other things that we've seen. So I like polar coordinates. It's nice. So how are we going to do this? According to this, we need to convert everything over, replacing our x's with this, r cosine theta, and then our y's with this, and then make sure we can get that r in there and change it over, put our limits of integration. We should be ready to go, right? So let's try it out. Z equals 3x plus 4y squared. Okay, we already have our region. I'm just going to draw it fast. So I'm going to put a little note here. This is a great polar region. Because it's polar, I'm going to try and get some control over what the angle and what the radius is for that region. So tell me about the angle. Every point that lies in that yellow region, the angle that you turn to get to any point in there must be between where and where? 0 and pi, right? 0 and pi. Now the radius means that every point that lies in this yellow region has to be stuck between what two radii? Well, the radius of the small circle, which was 1, right, and the radius of the big circle, which was 2. So your radius has to be between 1 and 2. So this is a rectangular region in polar coordinates. So I can already tell you right now that my double integral is going to be d. I can go d theta dr or dr d theta. It doesn't matter. I'm going to go d theta dr. I can already tell you this much, that the limits are 1 to 2 here, and I can say 0 to pi, right? That much I can say. I also know because I converted to polar, I'm going to absolutely have to remember that an r is going to pop in there, right? Times r is just sitting there, waiting for the rest of this to be resolved. What needs to go in here? Well, it's whatever the top surface is, right? And then the bottom, but the bottom is the xy plane, so z equals 0. The top is z equals this up here, right? But I have to convert to polar. So everywhere I see an x in that equation, I replace with r cosine theta. Everywhere I see a y, I replace with r sine theta. So just rewrite that up there. 3, what, r cosine theta plus 4 r sine theta, but I've got to square that. Crap, I didn't give myself enough room. Everybody good with that? Any questions? 3x plus 4y squared. Then your r's in there. Now let me just go ahead and clean that up, expand things out. Integral 1 to 2, integral 0 to pi. 3r squared cosine theta plus 4r cubed sine squared theta d theta dr. What happened here? Just square the r sine theta, right? Becomes r squared sine squared theta. But then I distributed through the r, so that's why I have an r cubed here. And then on the first term, I just distributed the r through and we're here. Right? We have two terms separated by addition, so I could split this into two doubles. You have a question? I distributed the r through here, and then after I figured out what this was, it came through here, and that's why I have r cubed and r squared here. Everybody okay with me splitting this into two doubles? No objections? I'm doing this kind of for a reason. I forgot my d theta dr over here. So I have two double integrals, right? Now, do you remember we had a theorem that said that there was a special case for double integrals, that if you had a double integral and you had a product where one of the factors was a function of x only and the other one was a function of y only, then you could split it up into two regular integrals and multiply the answers? Do I remember that property? Should I bring it up? Guess you don't have a choice now, huh? There it is. If your integrand was a function of x only times a function of y only, then you could split this into two separate regular Cal 2 integrals. Now, for us, we're not using x and y, but we have something similar here. We have r and theta, don't we? So if we have two factors that are completely, one in terms of r and the other one completely in terms of theta, we should be able to split it up also, which is what we have here, right? We could look at 3r squared as a function of r, cosine theta as a function of theta, and then just split this into two integrals. The one with r would get the 1 and 2. The one with theta would get the 0 and the pi. Yes? And the same thing over there, right? So this would become integral 1 to 2 of 3r squared dr times integral 0 to pi of cosine theta d theta. That right here is just this right here, right? Using that property on just that. Then you have to do the same thing over there. So I would have plus, because it's a different integral, right? Plus integral 1 to 2, 4r cubed dr plus times, right? Don't misuse the formula. 0 to pi, and then sine squared theta d theta. Can you integrate 3r squared with respect to r? Of course you can, right? Can you integrate cosine theta with respect to theta? Yes. This one? Yes. This one? Yeah. How are you going to do that? Do like a power reducing formula first. Turn that into like 1/2 minus 1/2 cosine 2 theta, and then integrate term by term. Each one of those can be done, though. So I'm going to put checks here. I won't take it the rest of the way, but I just wanted to see how you could apply that theorem, or that special case to that. Questions? And your answer is your answer. You don't have to convert back to Cartesian or anything. Your answer would be the same if you had left it in Cartesian. We okay with this? Yes. Yes. It's going to take the positive volume and it's going to take away the negative volume and give you like the total net volume there. Just get the total volume, like total volume, including the negative part is positive? Is that what you're saying? Like, yeah, you could, but you know, that's a good question. Everyone understand what's being asked? In this picture, is there a way to figure out what just the positive part of this is? You mean just this and not do this? How could he do it? Okay, you'd have to adjust your region to be just this region right here. You could not come all the way around, which means that your theta your restriction would be from 0 to what? Well, you'd have to go figure that out. And that might be a challenge because you're trying to figure out where that surface intersects the xy plane, which means you have to set z equal to 0 in this equation, right? When you set z equal to 0 in that equation, you would get 0 equals 3x plus 4y squared, right? And now if you go to polar, you get 3r cosine theta plus 4r squared sine squared theta, right? And now you'd have to solve this trigonometric equation, right? That's what you would have to solve. So what you could do is, my first instinct here, yeah, r is 0. I could factor an r out, which 1r, I can't get them both out of there. I'm debating, I think I want to switch sine squared theta over to, what, 1 minus cosine squared theta and get, I would have an equation that would be quadratic in cosine theta, and then I could solve, but my r is still in there. What I can basically tell you is that that looks like it's not going to be very clean. Like, I don't believe it's going to be like theta equals, it's going to be that actual line where it hits is not, it doesn't emanate from the origin straight out. It's some other weird line, and that is going to cause significant problems. So generally speaking, you're not going to be able to do it that. I mean, we ran into the same thing before we were in polar. If we ever wanted to try and figure out those negative volumes or the parts below or cut those off, we'd have to figure out where our surface hit the xy plane, and that right there would make changes to our region. So, good question. All right, so there's that one. All right, how about this one? Find the volume bounded by the parabola z equals 4 minus x squared minus z squared and the xy plane, the paraboloid. Z equals 4 minus x squared minus y squared. So it'd be nice if we want to do that, the volume of that, and bounded by that and the xy plane. So z equals 0. Do you all agree with that? The xy plane? So I need to figure out what the region on the ground is. That's my main goal here to set up the double integral. When we have 4 minus x squared minus y squared, we realize that that paraboloid starts out at 4 and then goes down, right? So it's like a parabola upside down, but it's three-dimensional. So going down, it hits the ground somewhere. So where it hits the ground, z is 0. So if I replace z equals 0 here and solve that, what do we get? So where this intersects the xy plane is when z is 0, which means 4 minus x squared minus y squared must be 0. And if I just move things around, that's x squared plus y squared equals 4, which is a circle in two-dimensional space, right? Circle, radius 2. So I know that wherever this thing hits the ground, it's like that, right? That's where that paraboloid comes through and cuts through the ground. So if I'm looking for the volume between that and the ground, then I really want the volume below that paraboloid and above that entire disk, right? The entire disk. So how can you describe to me what this entire disk is? Well, polar coordinates is great for that, isn't it? Wouldn't it be? In polar coordinates, I just have to find some restrictions on theta and r. So you tell me, what's my restriction on theta? 0 to 2 pi, go all the way around, right? What's my restriction on theta, on r? 0 to 2. I have a question, though. Could I have just gone between 0 and pi and let my radius go between negative 2 and 2? We haven't talked about negative radius, but just consider that for a second. If I want to draw this circle, and I said I want my theta to be between 0 and pi, and my radius between negative 2 and 2, then let's start out at 0. If I point out at an angle of 0, right, which means I'm going to point this way, and I'm allowed to walk out how far? 2, right, is the furthest I can walk out, but I can also walk out which way? Negative 2, so I can go backwards 2. Then that would give me everything here and everything here, right? Now let me say I can rotate a little bit. I can rotate between 0 and pi. So how about if I rotate and I point in this direction? I'm allowed to walk out how far? 2, and I can go backwards 2, right? And I can do that for any angle. Go up and then backwards 2. Up to pi over 2, backwards. And I keep doing that, right? But I'm only allowed to go to what angle? Pi and stop. What am I going to get? The same thing, right? That's another way that you could represent that polar region, is change your restrictions. Now, we very, very, very rarely do that, but I just want you to see you could still draw a disk with these restrictions. Now, what if you went 0 to 2 pi and negative 2 to 2? No, because you would actually be drawing a disk on top of a disk. So your region would be like overly defined. Make sense? You'd be drawing 2 disks. All right. Just wanted to bring that up, that you could look at it that way. But most of the time, I'm going to make sure our radius is positive. Okay, what now? I mean, I know I can go double integral, right? I know I can go 0 to 2. I know I can go 0 to 2 pi. I know I've got that r sitting out there waiting for me. I've got d theta dr. What goes in the integrand? Surface on top minus the surface on the bottom, right? Surface on top here is the paraboloid. Surface on the bottom is z equals 0. So I need to rewrite the surface on the top, which is this right here, replacing x with what? R cosine theta, replacing y with r sine theta. Now this is going to pop up quite a bit, so I want you to see what happens here before I plug it in. If I convert to polar, right? If I convert to polar here, 4 minus x squared minus y squared, you could go the long hard way and do this. 4 minus r cosine theta, cosine theta squared minus r sine theta squared. That's x squared minus y squared, isn't it? And then you could square each of those and go r squared cosine squared theta minus r squared sine squared theta. And then you could realize that both of these have an r squared in them, right? And a negative, in fact, r squared. So I could factor out just of those two terms, the negative r squared, and be left with cosine squared theta minus sine squared theta, right? Oh, not plus, sorry. Right, so pulling a negative r squared out of both of those, I would just get this, and that's what? 1, right? That's the cosine squared sine squared is 1. So this is just 4 minus r squared. Yeah? You could have done it that way, or you could have up here, you could have said, hey, wait, that's 4 minus x squared plus y squared, right? And remember that when you convert from Cartesian to polar, x squared plus y squared is r squared. It happens enough that I want to just point out, like, be looking for that sort of thing to happen. Be looking for the x squared plus y squared in there. Because anytime you see x squared plus y squared, it's r squared. In any event, this whole thing turns into 4 minus r squared in here, which is very nice. And now, yeah, I mean, we could do this all kind of in one step. Let's see, this is 4r minus r cubed d theta dr. Way off. All right. Look, y'all sign in today. Oh, this is the wrong one. I was like, what the heck? Y'all sign in today. Try and make sure you sign in on the correct date. There you go. Remember, you're allowed 4 absences, right? I know some of you have already exceeded the 4 absences. So if you're concerned about that, you should talk to me. Do we really need to go through this, or should we? I mean, it's up to you. It's your education. So, do you want to see the detail of this or not? We're okay? All right. Could you split that up, though, into 2 separate integrals and multiply them? I mean, do you have a function of r by itself with a function of theta by itself? Yes, you could. You would look at the function of theta as being what? 1. So you would have the integral for theta would just be integral from 0 to 2 pi of 1 d theta, then times integral from 0 to 2 of 4r minus r cubed dr. Multiply those 2 answers. Or you just do it all at one time. What's the antiderivative of 4r with respect to theta? 4r theta minus the antiderivative of r cubed with respect to theta would be r cubed theta. Okay, and then you just keep going. All right, I'm not going to show that. Next, note. Oh, by the way, this is the picture of it. There's the surface. There's the solid. We just basically found the volume of that solid right there. All right, so here things are going to change. All right, we're going to have a little adaptation. Instead of looking at, from the surface all the way to the ground, remember we could have something on the bottom. So instead of just the paraboloid all the way down, you could have the paraboloid and then maybe another paraboloid coming up, right? A different one. And if you do that, then what does it look like? I believe that's what my next example is. Yes. Oh, this is a good one. I'll show you the picture first. Find the volume of the solid below this. What's this? X squared plus y squared plus z squared equals r squared. That's a what? Sphere. That's a sphere radius 1. This right here is a cone. So you have this sphere, right? You have the sphere. You have a cone. Let me pull the sphere back. Okay, there's your cone. Computer did not like that. You're trying to find the volume of the solid between them. Give it a second to draw it. There it goes. Do you agree? That's what it looks like. Snow cone. What's the volume of that? Understand it geometrically. Okay, now we have to realize that we don't have the picture all the time. So sphere, cone coming up, you have to visualize that piece between them. And what the most important part of this is figuring out what the region is that you're talking about. So imagine, the cone goes up, it hits the sphere. Your region should be like the shadow of this thing straight down, shouldn't it? So if I look straight down from this, or on this like this, right? Straight down, my region needs to be this whole thing, doesn't it? It's not, the region is not the radius of the sphere. Do you all agree with that? Because if I bring the sphere in here, there's my sphere. My sphere goes out, all the way out to 1 in, each direction. So that can't be the region of integration because the cone comes up and hits it somewhere, and I don't want to look outside that, do I? So how do I determine what this circle is where they hit each other? Yeah, set them equal to each other, right? What we need, they hit each other means that their z coordinates are the same, right? That's where they hit each other. So you can basically set these equal to each other if you can solve them both for z. I have a better idea though. Why don't we just square both sides on this one, make that a z squared, and then plug that in here and just see what the hell happens. So I'm trying to figure out where does x squared plus y squared plus z squared equal 1 hit z equals the square root of x squared plus y squared. So first thing I have is that this means z squared is x squared plus y squared. I don't know. I'm just looking at this. I'm wondering, if you see this, are you going to want to replace x squared plus y squared with z squared? Is that what you would want to do? Or would you want to replace z squared with x squared plus y squared? What would your instinct have taken you to? You think you would replace z? Yes? With x squared and y squared? Now, let's just say we had replaced x squared plus y squared right there with z. Then you would get what? With z squared. You get 2z squared equals 1. Then you would have solved for z and you would have got 2 answers. And that would have told you, hey, it hits up here at a z up here and a z down here. That's what it would have told you. And it would have told you how high that is. But that doesn't tell you anything about that circle, does it? In order to talk about that circle, you need both the x and the y coordinates, don't you? So that's why you would want to not get rid of the x and y, keep them in the equation, and get rid of the z. So go in here and replace this with another x squared plus y squared equals 1. and then combine these things together, divide by 2, and therefore they hit at a circle radius. It's the radius of this circle. Careful. 1 over root 2, which is the same as root 2 over 2. Remember, the number on the other side is r squared. So we take the square root of it, and that's what r is. Yes? So when I look at the shadow of this region, right, my top function is the sphere, my bottom function is the cone, the region straight down from their intersection is this circle. I need to look at that and say, how do I want to make this double integral? I know what the top function is, I know what the bottom one is, but how do I set up the double integral? Do I want to stay in Cartesian or do I want to go to polar? So let me draw it. Here's my region of integration on the ground. Circle, radius is root 2 over 2. As soon as you see circles, I mean, you should immediately start thinking polar, right? I mean, that's the value of polar coordinates, is converting everything over so that you can handle anything that's on a circle like this. So polar, what's my restriction on theta? What's my restriction on r? 0, 2 pi? 0, root 2 over 2. I hope my wife doesn't listen to this video. She never watches my videos, so she packed me a lunch today. It's so funny. This never happens. Check it out. It's like I'm in grade school again or something. It's so funny. My lunchbox was like stapled together at the top so nothing would fall out. Cracks me up. These stupid things. All right. So I know this much. Double integral. I know that my radius is going to go between 0 and root 2 over 2. I should be more appreciative, huh? I'm grateful. I guess so. Well, can I just turn it over at the end and squeeze it too? Well, no, I'm just kidding. It's been laced with something. That's so terrible. Oof. I'm waiting for you here. We have a top, right, and we subtract the bottom. So that's what this note was saying. I know I blow through these things pretty quick, but this right here was saying you got your polar region on the ground. You got a surface on top. All the way to the ground was 0, but what if you want to cut it off on the bottom with something? So that's what we had. Our sphere was on the top, right? On the bottom was our cone. So our cone is forming the bottom of this solid. The sphere is on top. So if we want to do this, all we have to do is subtract the 2. Right? Subtract the 2. Now I'm going to do it with this one. I'm going to put them both in the same integral, same double integral. So you need to help me, if you could please, help me convert this right here and convert this right here over to polar. So we try and solve both of them for z, and then replace x with r cosine theta and y with r sine theta. So how about this first one here? Do you see what I see? What did we say x squared plus y squared would always be? R squared. So if I'm going into polar here, then this is going to be r squared plus z squared equals 1, right? And if I solve for z, z squared equals 1 minus r squared. and z then must be square root 1 minus r squared. So that's my top one, right? Over, or not over, the one on the bottom, okay, is this one, z. Convert this one to polar. My work is always much neater when I'm doing my own work. I'm always trying to fit everything onto one screen here for you. That's why I'm always going everywhere with everything. I hope your work's a little bit nicer. This one right here, convert over, what do I have? The root of r squared, which is just half the value of r, which is r is positive here for us because we restricted it positive. So it's just r. Z is r. And now, come back down here and plug those things in. We've got root 1 minus r squared minus r. And then remember we had the r, right, in here? That r is going to distribute through. The r will go in front of the root, and this will become r squared. So I have integral 0 to root 2 over 2, integral 0 to pi. I have r root 1 minus r squared. Are you happy that that r was there for that one? Do you see it how I see it? If you had to integrate this one right here can go with the basic substitution now. A u substitution of 1 minus r squared. The derivative of it is out here, kind of. So that will be a basic substitution. This one, not even worth talking about. And then it should be pretty clean. When it's time to integrate this, it'll be nice. Dot, dot, dot. So possibly part of the challenge of that is that visualizing it, understanding, the sphere and the cone, and like trying to figure out what that region is going to be, where they hit. Any questions? All right, now everything I've done up to this point has been a polar rectangle, right? We've been lucky. Our theta has been between two constants. Our radius has been between two constants. Yes? But just like we had with rectangular and Cartesian, we then start talking about type 1 and type 2, right? Like what if the x is between two constants but the y is between two functions of x? Or we said type 2, where what if the y's are between two constants and the x are between two functions of y, right? Well, with polar, it's the same story. What if we have a situation where our theta is stuck between two constants, but our radii are not stuck between two constants? Our first radius is actually a function of the angle. So imagine it this way. I'll give you a real quick example of a polar function where the radius is a function of theta, a polar curve. Sketch r equals cosine theta. So if you look at this, you could almost do it like a t-table. You could say, here's theta, here's the radius. So let's plug in 0. Cosine 0 is 1, so the radius would be 1. Let's do something like pi over 4. What's cosine of pi over 4? Very good. I didn't hear anything. Root 2 over 2? Yes? I need more than that. It's going to be, might be too difficult to see this. Let me add one more in there. Cosine of pi over 6. Root 3 over 2. Cosine pi over 4, root 2 over 2. Cosine pi over 3 was 1/2. Cosine of pi over 2 was 0, right? And I could keep going with this. Now, how do I draw that curve in polar coordinates? The first point, I point in a direction of 0, which means I point out the x-axis. And I walk out how far? 1 unit. This is the polar point 1, 0. Right? Radius 1, angle 0. The next point, what I do is I aim at an angle of pi over 6, right? I aim at an angle of pi over 6, and I walk out how far? Root 3 over 2. So pi over 6 like this, and I walk out root 3 over 2. I'm here. And then pi over 4, I'm up here. And then keep going, right? And then keep going. And what am I drawing? I'm drawing the unit circle. So if I draw this unit circle, which is terrible, my radius is a function of theta, isn't it? Yes? But it's always, my radius is always the same, isn't it? I mean, like, the radius is always, what's that? Oh, wait, hold on. Go back. Just had a major brain fart. Hold on. Y'all let me do this without, why'd y'all let me go all the way there? Hold on. Let's go back to this. At pi over 6, I go out about root 2 over 2, right? Root 3 over 2. And then at pi over 4, how far? Root 2 over 2. Is that bigger than root 3 over 2 or smaller? Smaller, right? So I don't go out as far. And then what about at pi over 3? So I'm aimed this way. How far do I go out? 1/2, which is here. And then at pi over 2, I'm pointed straight up and down. I do what? My radius is what? 0. I'm here at the origin. So what I've actually drawn is this. That's what I've drawn. My curve, my radius, is a function of the angle. So initially my curve's out there, but as I start to rotate, my angle changes. This thing's coming back towards me, and then when I'm straight up and down, it comes all the way back to me. And so, do y'all see that? It's kind of a critical graph. Instead of the difference between that and this, which I'll transpose on top of it, if I just fix my radius at 1 and swing, then that radius is fixed the whole time, right? This radius here is not fixed. The black one, the equation for this curve in polar coordinates is r is 1. That's the equation of that one. R is 1. Your radius is always 1, no matter what. Any angle, you turn, you look, and it's 1, right? So the question now becomes, if we have, I hope this illustrated things, didn't make it more confusing. If we have a curve that instead of just holding a radius the whole time is actually fluctuating and changing as we turn, and we have another one on the outside that's doing the same thing, then can we then determine still the double integral above that region? And the answer, of course, is yes, right? Our theta is between two constants. Our radii are between two functions of theta. And so your double integral looks like this. Theta is between two constants. The radius is between two functions of theta. And therefore, your double integral convert from Cartesian to polar. You have your constants are the outer integral, alpha to beta. That goes on theta. Since radius is the one that's being stuck between two functions of theta, that's the inner integral. That's with respect to dr, or with respect to r. And then, of course, we always have that r that pops in there, right? This order of integration cannot be changed. Just like with type 1, type 2, you couldn't just change them when you wanted to. So we can't change this order of integration. We're stuck. Now, let me see. Can I see your quiz again? I want to make sure I don't do the exact quiz problem. You lost it? You lost it already? That's a good one. That's a good one. Okay. Find the volume of a solid ball radius 4. Has been drilled out with drill bit radius 1. Drill bit ran. This is so close to your quiz problem. I mean, I don't even... Hmm? I'll do something a little bit different. I'll change it just a little bit to see how you deal with the change. All right? Oh yeah, by the way, yeah, I posted this on Canvas last week? Friday? Thursday? Friday? You asked about the due date, right? It's next Monday? Yeah, that's right. It's just, we don't have class Wednesday. Yeah. Yep. All right. So look, a sphere of radius 3, it's actually a solid ball, okay? A ball of radius 3 has a cylinder of radius 1 drilled out of it as shown below. So, let's see. There's your sphere, right? I'm going to take a cylindrical drill bit and drill through this thing. When I do that, I'm going to get this, right? Get this hole in this ball. But you can't just find the volume of the cylinder you drill out, right? Because it's not the top part of the cylinder is not flat. Where it cut out the sphere, right? Like right up here. That cap up there is kind of rounded. Do you agree? It's part of the sphere. So we're drilling out. Let me see. I don't remember what this animation looks like. Here's a cylinder. There's a drill bit right through the thing. Pull this out of here. I don't remember what all the hell this stuff is here, so let me see. There we go. I know what that is now. All right, that's the part we drilled out, right? Y'all agree with that? If I look at just the top half of what we drilled out, it should be symmetric to the bottom half, right? What we drilled out. And the color is not real good here, but let's just try this. I don't think it really works to help you see it. I'm trying to show you that that top part of this that got drilled out, you know, is kind of rounded. It follows the contour of the sphere. Yes? So we want then to figure out the volume of the entire ball, right, which is what's being asked. It says don't evaluate the integral here, by the way. It wants us to, well, I mean, we could find the volume of the ball, right? We already know, we have formulas for the volume of a ball. And so we can figure that out because we know the radius already, right? Figure out what that is, and then subtract from that whatever this volume is. And to do that, we could just find half of that volume and double it, right? And then subtract it. So what, in terms of like calculus language here, and not without being too technical, what is it that I'm looking for here? This red thing? And like, trying to get back to my original zoomed in here. There we go. That red thing would be the volume of the solid that is below the sphere, above z equals 0, the xy plane, right? Between the sphere and the plane. On what region? What's your region on the ground? What's your shadow on the ground? This circle, right? It's circle. But there's a problem, because that circle is not centered at the origin. And therefore, it's not in a perfect polar region. Perfect polar region for us is when the radius can be stuck between two constants and the angle between two constants. If you have a circle centered at the origin, then the angle is 0 to 2 pi, and the radius is between 0 and whatever the radius is. In this case, the drill bit has a radius of what? 1. So that would be simple if it was right down the center of the sphere, or the ball, right? But this is not drilled down the center, is it? Can you tell from the picture that that drill bit, I kind of kept it parallel to the z-axis the whole time, straight down? So the drill bit is touching the z-axis was, I think you understand. The drill bit's coming in here. It's always running parallel to the z-axis the whole time, and then back out. And you could say it was like tangent to the z-axis. Make sense? So that changes things, doesn't it? So let's try and get our head around this polar region on the ground first. Then we'll figure out the top and bottom. But generally speaking, I think we have the basic idea. We've got sphere on top, plane on the ground. We just need to figure out the shadow. And then once we got that, try it in polar. So I'm going to choose to do this a certain way. And on your take-home, you can't just mimic exactly what I do. I want you to do something a little different. I'll tell you, I'll guide you to it, all right? If I'm looking down, right, here's my sphere. That's the ground. That's the XY plane. My drill bit came through here, and I could say, since it had a radius of 1, if I went up here to 1, and this being 2, then my drill bit comes in here like this, right? It's the worst circle I've ever drawn, but you get it, right? That didn't work. That didn't help. All right, so there's the drill bit, right? Running down the z-axis, coming back out. All right, so now I need to figure out if I can look at that as a polar region or not. So imagine, if you could, that when I'm pointed out, like I'm trying to figure out my radius, is it a function of theta? If I point out to the right, down the x-axis, what's the radius? 0, right? And then if I turn a little bit, the radius is this, right? If I turn a little more, the radius is this. Turn a little more, the radius is this. And then it's this. And then it's this. And I keep going around and around and around, right? Until I get where? What angle? To pi, right? It looks like that polar region will only exist between 0 and pi, right? Make sense? The radius is some function of the angle I'm at, and I'll figure that out in a second. But I just want everyone to see that my theta looks like it appears to be between 0 and pi. What the actual radius is, we'll work on it. Now remember, we said that this idea that our theta is going to be between two constants, our radius, we're going to have an inner radius and an outer radius, both of them functions of theta. I can tell you that this is the outer radius right here. The inner radius is always what here? Like, I guess what I'm trying to get at is this. My radius should be bounded between two functions, right? Two functions of theta. But I can tell you right now that this radius, that radius, all of the radii here are all between whatever that radius is and what? All the way back to the origin, 0. So I know that the radii are stuck between 0 and something. What is that something? So, what's that? Well, the thing is, it's only 2 when I'm pointed straight up, right? When I'm pointed straight up, so when theta is pi over 2, yes, you're allowed to walk out 2. But when theta is something different, you can't walk out 2, right? These numbers are smaller than 2. Go ahead, Josh. Maybe sine? Sine theta? Maybe, I don't know. So how are we going to get it, right? I mean, we need a way of getting it. So the one thing we should remember is that we know the equation of a circle centered anywhere with radius anything in Cartesian coordinates, right? The general equation is x minus h squared plus y minus k squared equals r squared. That's your general equation of a circle centered at hk, radius r. So what's the equation of that particular circle? in Cartesian coordinates. So what's the center of this circle? 0, 1, right? That's h, that's k. So the equation for this particular circle should be x squared plus y minus 1 squared equals, what's the radius of this circle? 1, right? Everyone agree that's the equation of that circle? What I'm going to do now is attempt to get this thing converted over to polar coordinates. So I'm going to go ahead and expand out the y squared, or y minus 1 squared. You agree with that? Do you see it? See something really, really good just happened? The x squared plus y squared is what? This is r squared. Minus 2, now convert y into its Cartesian. R sine theta, right? That's minus 2y. And then you have the 1 and the 1 on both sides, right? Cancel them out, and you get equals 0, don't you? Everyone see where all that came from? Now, take this equation and solve it. So let's factor an r out. You agree? Factor an r out. And now set each of these factors equal to 0. So the first one, we get a solution of r equals 0. And the second one, we get r minus 2 sine theta equals 0. Yeah? Well, r equals 0. Remember we said there was going to be two equations, like one of them is the inside, the other one's the outside. R equals 0 was that inside one, wasn't it? And then look at this one. Solve this for r. Move that over to the other side. And what do you get? R is 2 sine theta. So you were real close on that. Sine, real close, but it's 2 sine theta. Because it goes to 2, right? And you can always check this, right? We knew it could be any angle between 0 and pi, so let me just real quick on a table. Here's theta, here's r. I'm using this right here. I'll do 0, pi over 4, pi over 2, 3 pi over 4, and pi. Let me just see what happens. Sine of 0, 0. Sine of pi over 4, root 2 over 2 times 2, so root 2. Sine of pi over 2, 1 times 2, 2 is 1, is 2. Sine of 3 pi over 4 is root 2 over 2, then times 2, so you get root 2 again. And then sine of pi is 0, so this is it right here, right? So if I tried to draw that, if I aim out at an angle of 0, that means to the right, right? Aim out this way and walk out how far? Nowhere, so just stay at the origin. Then aim at an angle of pi over 4, which would be aim this way and walk out how far? Root 2, which is like 1.414 or something like that. So you would be out, let's just say here. And then at pi over 2, which is straight up and down, you walk out how far? 2, which would be up here, right? And then another point would be here, and then you'd be back at 0. So that's what we would have so far, right? 1, 2, 3, 4, 5. Right? Yeah, there's 2 zeros. So to pick up more detail, I would have to go to a different angle, like maybe pi over 6. If I do pi over 6, I'm going to wind up being somewhere like, it's going to be like here, and then over here, and then here, and here. And then when you put them all together, you're going to get the circle, right? That's what would happen. Make sense? So, my region that I'm talking about here, my theta is between 0 and pi. My radius is between 0 and 2 sine theta. So my double integral is going to go from 0 to pi, then 0 to 2 sine theta, And then over here, R, this order matters, dr d theta. And now I need my integrand. So we had the top and then the bottom, right? What was the top one? What was the top of that? It was the ball, right? The sphere. So you go to the equation of the sphere and convert it to polar. What was the bottom? The xy plane, so z equals 0, right? So I don't have to look at that. And then remember, we're going to double the answer, right? Because it was only that red part that we cut out. We're going to double that. So because theta is the one that's between two constants, so it has to be the outer integral. When these two were both between constants, the order, well, you had to match the r's and the thetas up, but we could have switched the order here and switched the integrals here. All right. So you take the equation for the sphere. What was it? I forgot. Theta. Uh-huh. That's right. Yep. Another way you can think of it is the thetas between constants. That has to be the outside one then. Okay, so the equation of the sphere would be x squared plus y squared plus z squared equals r squared. What was r for us? Radius 3, so 9. Can you solve that for z and go to polar? What's this going to be in polar? R squared. Take it to the other side and take the square root. So you get z equals square root of 9 minus r squared. Yeah? And that goes in here, right? That's another u sub. Because that r that's out there, right? This r out here would come in next to that, and it's a u sub. That sets up almost exactly like number 5 on your take-home. So any questions on this? I'm not going to go any further with it. Just be careful when you do your antiderivative. You have to go with respect to r first, figure out what that is, and then after that, you go plug in this for what? These two go in for what? For r, right? For r. That might actually be a pain in the ass. We should look at that. We should look at that. The first integration should be okay, but let's see if that second integration works or not. I think that's why on your problem might be a little different. Let me see. Yeah, hold on. I'm just thinking about this. I'm hiding the answer from you real quick. Because I don't want to do this problem. Don't auto switch on me. I know that's what you're doing. Okay. There. Get ready, and here it comes. No. What did I give you on that again? Let me see yours. thought I had changed it. Okay, so I'm going to have to change number 5. So I'll work through this one, and then I'll show you we're going to change number 5. We're just going to change it to a different, instead of a ball, we're going to drill through something else. What we drill through will be much, much easier to integrate. But let's at least appreciate the fact that this is never going to come back on. There we go. Whoa. Yeah. Okay, so okay, let's see where this takes us here. So I'm going to integrate this, all right? Right here. Have you all already started working on it while I'm sitting here? No? All right, so I'm going to just move that R inside here like that. Get rid of it out there. So I'm going to make the basic U substitution. U is not square root, 9 minus R squared. Du then would be negative 2R dr. I multiply negative 1/2 du is R dr. So this integral inside, this inner one, is going to transform into the integral. I'm not going to put my limits out there. It'll be negative 1/2 square root of u, which would be u to the 1/2 du. Understand that? U substitution here. Then integrate. So you add 1, so 3/2 and then 2/3. So 2/3, that would be negative 1/3 u to the 3/2 would be the antiderivative of this. Double check it, take the derivative, you should get this. Now replace u with what it was. U was 9 minus R squared and then to the 3/2. But you're now supposed to plug in what into this? R is 0 and R is 2 sine theta. And when you do that, this is where things start to fall apart. Because when I plug in 0 here, I just get a constant, right? So I'm not worried about that. But when I plug in 2 sine theta right here, I get negative 1/3 9 minus 4 sine squared theta to the 3/2. Could you integrate that? Maybe. That's going to be a lot of work, though. It's going to be a lot of work. It works to the point that I think even Mathematica may have a problem with it. Let's see. Whoa. Oops. Okay, we're trying to integrate square root of 9 minus 4. Ooh. 9 minus 4 sine x squared dx. I know I'm using a different variable, but that's it, right? That's what we're trying to do. And then there's a negative 1/3 out there. Oh, yeah. All of that. Oh, to the 3/2. I still, yeah, just take that and cube it, right? Raising to the 3/2 is same as doing the square root cubed. I don't think it's going to change. Yeah, it's even worse now. So it's giving you the elliptic error function. And so that is not something you're going to be able to integrate by hand. Okay? Now, could you get a numerical answer for that? Absolutely. Numerical answer, you could use like a Taylor series, power series, and go as far as you need to integrating term by term. I'm just saying that, I mean, it seems like maybe you'd want to someday drill a hole, someone wants to drill a hole out of a ball bearing or something. Who knows, right? Like, it would be nice if they get an answer. You can. This just says that getting the antiderivative by hand in a nice closed form is going to be very difficult. So that's why you can't do that problem. That's why I said in this, I said do not evaluate. Just set up the double integral. So to resolve that on the problem for your home, what I'd like for you to do is a little different. Okay, here's what I'd like for you to do. So please scratch out that, just scratch out the whole problem, okay? Here's what we'll do instead. Instead of doing a ball and then we drill out the, like, you know, parallel to the z-axis like that, let's do something like, there we go. That's a good one right there. Something like that, so I don't have to draw the whole damn thing. Same exact idea. You have a drill bit. The drill bit has a radius of 1. Where did I say the center of that drill bit went through on that problem? 1, 0, 0. Okay. So same idea. You have a drill bit, radius 1. You're going to drill through this paraboloid thing. All right? The good news with this is that in the past problem, right, when we tried to solve for z here, we got square root of 9 minus r squared, didn't we? Square root of 9 minus r squared in the problem with the ball was our integrand. When you solve this one for z, you will not get square root of 9 minus r squared. You're going to get something a lot cleaner. It's going to integrate a lot better. Now, the second time you come through, though, and you replace the r with whatever sine theta or whatever it turns out to be for you, that integration is going to be a little bit of a pain in the ass, but it can be done. It's just going to kind of suck a little bit. Okay, so everyone understand that on number 5, we're doing that paraboloid, the ground, drill through. Your drill has radius 1. You are not allowed, okay, you are not allowed to use the same diagram that I used today. So what I would recommend is instead of coming through with your picture like this one, just move your drill bit over here instead. I said the center of it's supposed to go through 1, 0, 0. So what I was trying to get you to do is force you to have your drill bit go through so that the center is 1, 0 right there. So it has to be on the x-axis. Let's just all do that, and that way we're all on the same page. We all get the same work. Okay, everyone understand? You got your paraboloid, you're coming through, drill bit comes through like that, comes back out. Yes? Questions? I believe this ends double integrals in polar. And we're pretty much out of time. Where are we going? Applications is next. Density, mass, electrical charge, moments center mass, moments of inertia. That'll be quick. We'll knock that out in probably about 15 minutes. Next class, 20 minutes. And then we'll get into triple integrals. So think about it this way. A double integral, what was your region of integration? In a double integral, your region of integration was on the ground, right? So in a double integral, you're getting a volume, which means that your region of integration is an area in two-dimensional space. In a triple integral, you're getting, well, you can't talk about volume because you're no longer in three-dimensional space. You're actually finding what we call like a hypervolume. It's a four-dimensional volume. It doesn't make a whole lot of sense geometrically, but the important thing is that your region of integration is now three-dimensional instead of two-dimensional. So double integrals, your region was area flat on the ground. Triple integrals, your region of integration is three-dimensional solid. So just like we had to figure out for our two-dimensional region, like what's our limits on x, what's our limits on y, we could do type 1, type 2 rectangle, go to polar if we wanted to. Now imagine that that region that you're integrating over is a three-dimensional solid. How many different ways can we describe a three-dimensional solid? Think about just a basic box. The x's are between something, the y's are between something, the z's are between something. All three variables between constants, you're integrating over a cube basically. That'll be the easy case, and then we got to get crazy with it. And we're going to go into we're going to go into what are called cylindrical coordinates, which will be another coordinate system that we use. It's kind of like we did polar to help us out in 2D. We use cylindrical to help us out in 3D, and then there's another coordinate system in 3D, spherical coordinates. So we'll use Cartesian in 3 dimensions, cylindrical in 3 dimensions, and spherical in 3 dimensions, and triple integrals. So, and then you could go further. We don't go any further, but I mean, you can imagine you could just keep going and figuring out, four quadruple integrals. And I remember an integral that I had somewhere in a stats class way in grad school. It was like, I don't know how many integrals were in that problem. It was like a infinite summation or an infinite number of iterations of integration. It was weird. Okay, y'all want to leave? Let's go. What are you doing for homework? Your take home, right? Okay, there weren't any problems at the end of that. I'll send out an email that if you want to practice some problems in the book, I'll send something out so you have something to go off of. But get that take home done. Have a good weekend. Wow, I don't say that on Monday very often.